Alrighty, hello YouTube. Um, Thanks for watching. I want to show you what I did here to improve this Madison. I did a bunch of things, but I'm just kind of taking a break, maybe a permanent break, I don't know, from this rk56. Um, and I'm going to do something that's a little bit easier for me to do at this point in time. And one of the problems I ran into with this Madison was a mic gain issue with the unit not having enough mic gain. So when you're trying to use a Turner Road King mic, for whatever reason, Road Kings are not really great at output voltage, and they can be a real problem on some radios, and they seem to be a real problem for the Madison. Now, unfortunately, I just want to make one comment, and I think this is true. On the older Madison, I think this would be much less of an issue than this newer Madison that I have here. Because the older Madisons have a different mic gain or a mic amp circuitry in them that looks to be a much better way to do things. So I had to kind of reinvent the wheel with my Madison, and I actually tried doing some internals to the radio, and I didn't really have any great success. So as a last resort, for anybody that's interested in getting a Madison, I can tell you this. I would recommend getting the old flip clock version of the Madison, and I'm just basing that on, not that I've ever owned one, I wish I would have one. I'm just basing that on what I've seen with the schematic, some things that I've seen on the schematic to the old Madison. So just FYI, and I hope that I'm not selling myself out by saying that, because I really do want an old Madison. Now this Turner here has been a real bunch of crap all on its own. They just aren't made the way they used to be. After about 2 weeks with OCD, it kind of canceled out my screws. So the only way I can get the screws to back out is to fight with them. This is definitely not made like an old Road King, I can tell you that much. So how do we get some more mic gain if we want to invest some time? Right here is the answer. Take a gander at this. I tried many different ways to do this, and my last resort was to do it in the mic. I didn't want to do that for reasons that I'll probably get into here. So I have 2 nickel metal hydride, I think they are, that I just ordered from eBay on here, and they're 3.6 volt. Now interestingly, originally I had this garage door opener battery in it, and surprisingly the garage door battery did very, very well. It did much better than I thought it would, but at the end it kind of got challenged once again by the OCD, because you know, that's what it does. It makes you take something that was probably fine and tear it all apart and throw it away, and then build a new one to try to make it better. And you know, long story short, I've done that 4 times in this mic. But this garage door battery held up much better than what I thought it would. I thought the current drain on it, even though it was probably only oh, what was it on my initial one? I think it was like 3 milliamps. I thought, you know, this garage door battery is going to croak after several days. It held on real good. So just FYI. But now we have some 3.6 volts in here. And I tied them in series. And I check this every day because this is an ongoing test to make sure that there is not leakage current flowing from these batteries back into the transmit receive switching in the Madison. So I turn the Madison on and leave it powered up, leave the mic plugged in, just to make sure we don't have leakage current, because internal to the Madison, and it's probably true with some other radios as well, what they do in order to initiate transmit is they pull the emitter of an NPN down back to the common, which I have the black wire here being common. They pull the red transmit wire back to the common and ground that emitter of that transistor inside the radio, which connects to the MB voltage regulator that initiates transmit. So it's a reverse bias junction, but I just wanted to make sure that there is not leakage current flowing in some place that I couldn't precipitate, because, you know, schematics can be tough sometimes. But anyway, that's what I got. Take a look at this guy. I have a an OPA 1642 high fidelity op amp from TI in this Turner mic. And I think it's funny to note, and this is like a 35-minute story that I'm not going to get into, but originally I took the Turner element out and I put a Heil HC5 element in this mic, and I ran that, and they said it sounds like absolute garbage on that Heil, and I just kind of chuckled and put the Heil in the bag, and you know, make of that whatever you want. An HC5 element, and it sounds like garbage. So I put the Turner element back in, and I've changed this around like 100 times. So there's an op 1642 there. There's a low ESR ceramic bypass chip here on the power, and I think I have a 47 mic in there right now. This is biased at half of VCC, or half of the battery voltage, up in the air on the non-inverting terminal, on a non-inverting, which would be pin 3. Pin 2 would be your inverting terminal. So it's biased halfway up in the air. So just to show you basically what I have here. So taking a look at this on a piece of paper here, really no science to it. So we got 7.2 volts of battery. This op amp here I checked will run down to plus or minus 2.4 volts, which is pretty low. So 7.2 volts is going to be fine for it. Might be able to push it a little bit lower, but it kind of ran into fitting a battery in there issue, and with the voltages and stuff. So anyway, so there's the 10K pot. There's a 1.1K there. I just used that because I had a whole boatload of them left over from a Sansui Sansui project that were actually precision resistors. 750 there. And this guy is AC grounded through a 47 mic there. And then this is DC blocked through that 47 mic SMR Kemet PPS, which is is kind of crazy to have in there. That's a really super expensive cap. And I think there's something with these groundings. I don't think all these grounds are tied common to each other, but for simplicity's sakes, I'm just going to make them common. And there was our original cap, coupling cap, or it's not even really a coupling cap. I don't know what you would call it, that Turner had in here, where I changed it to a one mic at one point in time. I just kind of left it in there, but it doesn't actually even need to be in there. And there's actually a 22K in here to ground that doesn't need to be in there anymore. It was there because I was actually feeding this output directly into the radio rather than feeding it into the transformer here, but it really doesn't serve any purpose. And then this eventually goes out to your audio line. And this was the original transformer that was there. I'm just trying to think if I missed anything. So the voltage gain on a non-inverting op-amp, just to try to give a real quick tutorial. It's really something good to know, the basics of op-amps, because you can really build upon them. But the voltage gain on a non-inverting op-amp will always be 1 plus RF over Rn. And I'm by no means a teacher, but so there's our RF and there's our Rn. So I'll do this. Maybe this can be helpful to somebody that doesn't know much about op-amps. So we got 11.1K there in the feedback, divided by 750 ohms. So we have a voltage gain of 14.8 plus 1. So we got a voltage gain of 15.8. when this pot is turned the whole way up to 10K. Now the next part here was the roll-off, and this is something that I ended up doing based on experience. Typically you don't see 2200 picofarad capacitors across an output for high frequency roll-off. That's a really insanely high value, and part of the reason for that value being so high is because this pot value is so low. But that's what I had to work with, so that's why I ended up with that. And I set that at 6K to roll off. So at 6K, we're going to be down by approximately 6 dB. So I'll just show you one other thing here that's pretty cool. Might be helpful. Doing a little bit of backwards engineering, which is the way I did this. I just mentally went in my head and said, okay, I want to roll off 6K. How much reactance do I need to manipulate this resistance here? Because as we change this resistance, we change the gain. And as we drop this resistance here, we drop the gain. By the same token, if we drop the resistance here and left that the same, we would increase the gain, if you follow my madness here. So I substituted in 2200 to come out with around 6K, but I'll just do a little bit of math here real quick to show you how that works out. I don't know if I had enough caffeine to counteract the sleep, the lack of sleep here, but we'll find out in a minute. So we want to figure out the reactance of that, so we'll just substitute in 6,000, 6 kilohertz. Yeah, sleep deprivation is definitely showing already, because it took me a really long time to get that into my head as to what I wanted to do. Normally I can speed through this calculator like it's nothing. So the capacitive reactance of that is basically 12.063K. That's what we're going to get. So as we start to roll this up in frequency, when we get to 6 kilohertz coming into this guy here, this reactance here is going to be down to 12K. And when that goes to 12K, 12K across that. So essentially what we have is 11.1K, and then we have the 12K, which is our reactance, across that. So we want to find out what the total resistance of that is going to be. So we just take RT equals R1 times R2 over R1 plus R2. Really basic stuff. If you know the basics, man, you can take this stuff much further than you ever dreamed of. So 11.1K times, well, actually I should have did it the opposite first. I want to do the addition before I do the multiplication, because I won't be able to correlate that in my head to do that. So 11,100 plus 12,063 is equal to 23,163 ohms. And we kind of store that away for a second. That's our R1 plus R2 there. So now we take our R1 times R2, which is 11,100 times 12,063, and we get a big, huge, gigantic number, divided by 23,163. So now we have a total feedback resistance of 5.78K. So you can see what happens here. If I can get this to go. So now this whole section here has now dropped to 5.78K. So the gain has went down by the reactance of that capacitor versus the input frequency. So now to go just a little bit further with it, the voltage gain was 15.8 when there's actually no reactive component by this capacitor, meaning this frequency is low enough that it's not reacting with it. So given a voltage gain of 15.8, we can calculate our new voltage gain at the 6 kilohertz point where we start to roll off. And all we simply do is take our, see if I can correlate camera to paper, take our 5.78K and go back and plug it in for our voltage gain and divide it by 750. So now we got a voltage gain of 7.7. If this frequency were constant at 6K, that would be our voltage gain. So you can see it fell off significantly. And I don't know if I stated this, the reason I do stuff like this is because sibilance can be a real problem with the S's and the T's. When you get into professional recording and stuff like that, sibilance can always be an issue. So you don't want S's and T's coming through any more than you have to. Sibilance is, and I'm not an expert by any means, but I just give you the basics here. Sibilance typically happens at frequencies generally around 6K. They can happen a little bit lower than 6K, and they can travel the whole way up to about 8 kilohertz. Just FYI. So looking at our voltage gain, let's kind of calculate how many dB 6K fell off on this guy. And that's pretty easy to do. because all we have to do is just take this voltage gain and look at this like this were a real actual volt number, a realistic reading, if you will. Say we put 1 volt here, and this op amp had no problems. It had an indefinite rail, and it could swing anywhere it wanted to swing and be happy. If we put 1 volt here, it's going to sling to 15.8 volts. So we'll just call this 15.8 volt voltage gain a real number. So we'll take 15.8 and we'll divide it by what the gain went down to, a voltage gain of 7.7, which we're going to make into a realistic number of 7.7 volts. And that's what you come up with. And I'm actually getting ahead of myself here because the formula for this is voltage gain equals 20, and it's the logarithm of V out over Vn. V out is our reference point that we started with, which is the voltage gain of 15.8. Vn is our reference point of where this thing starts to roll off at, and that's 7.7. So when we take this and divide it by 7.7, we get that. And when we take the logarithm of that times 20, oops, what did I do here? 15.8 divided by 7.7 log times 20. Yeah, I don't know what I did. I mentally blacked out, and the calculator just followed me. So we have 6.4 dB is what this rolled off at 6K. So man, if that didn't turn your brain to mush, you know, I don't know what to say. So there's the cool factor of this. Let me pan out and come back into a realistic world here where I can see things right. So there's a little bit of a tutorial. You probably got more than you bargained for. I hope you were able to follow all that madness, and I hope it makes perfect sense to you. It takes a little while if it didn't, but if you do it a couple times, you'll see the madness to it, and you'll say, man, that was so simple. You know, I can do great things now with op amps, just knowing those basic things. And those basic things are that figure there for a non-inverting op amp, and for an inverting op amp, meaning that the input signal is applied here, it's even easier because it's just simply RF over Rn. So a non-inverting always has to have a gain of more than 1 because there's an addition factor of 1. Where an inverting op amp can have a negative amount of gain to it, if that makes any sense. And this here is a very wonderful formula here for voltage gain, 20 log V out over Vn. I mean, the sky is the limit with that cool formula. And there's just one more. If you wanted to do power gain, power gain is a 10 log function of P out over P, or yeah, I did it again. Went to write a P and wrote an R. And you can use this cool formula for a number of things. Let's say you got 100 watts coming out of a transmitter and out of an amplifier, and you're putting 10 watts into it. What's the power gain? So I know the answer to this, but if you have 100 watts coming out and we divide it by 10 watts coming in, and we take the log of that times 10, the answer is 10. So we have 10 dB gain from that amplifier. So you can't confuse power gain with voltage gain because they're two different applications of the log. So anyway, I rambled enough. So I'm not going to drag scopes out and stuff to show an envelope, but hello radio, 1 2 3 4 5, 1 2 3 4 5, hello, 1 2 3 4 5. So I got that mic gain cranked up there pretty good. If I turn the mic gain back to halfway, hello radio, 1 2 3 4 5. That's 2 inches away from the turner, and you can see that we don't have an envelope. Hello radio, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5. Now if I eat the turner, I can get an envelope at half mic gain. And if I give it 3/4, hello radio, 1 2 3 4 5, hello, 1 2 1 2 1 2. That's 2 inches from the mic, and that's full envelope because the ALC is set at 12 watts on this radio. So looking at this old diamond here, you can see where 12 watts should be, hopefully. Don't know if the lighting's good enough. Hello radio, 1 2 3 4 5, hello. So right there's full envelope. 3/4 mic gain, and I am not by any means a loud talker at all. So hey, hope maybe you stuck with me, and man, that would be great. Appreciate you watching. Have yourself a wonderful day.